Our next talk is by Devavrat Shah on causal matrix completion. Pray tell us about that.
Thanks, Chris. Very nice to be here in person. My first conference talk, I presume. Similar openings you have heard many times now in person. So this is based on joint work with Anish Agarwal, who is a graduate student at MIT, Manzar Dale, who is my colleague at MIT, and Dennis Shen, who is sitting here in this purple mask, and who is now who finished his PhD from MIT, and now he's a postdoc here with the part of the FODC program. So here is the outline of the talk. Of course, please feel free to stop me. This is one of those nice human talks, so that interaction would be extremely valued. I don't have too many things to go through, so of course that'll help anyways. And I think I have till 11.
Yes. Okay.
Or
2.
Thank you for the +2. Yes. So I will first just quickly remind us what the matrix completion question is. Of course, it's come up in different forms. For example, in the last talk, it came up through in a form as a stochastic block model. We'll quickly remind the question, give few examples, few of my personally interesting example, just arguing that, you know, it's on one hand, there's a typical view of matrix estimation, but maybe it can be a more interesting subroutine than just the way we think about it. Next, I will spend some time discussing the model. Again, so there's a signal and there is an observation, and it's an observation part where causality comes in, and I will spend quite a bit of time discussing that. Briefly, I'll do a literature review. There's a massive literature here, so I won't be able to do justice, but I will try to at least touch the highlights in terms of algorithms and the results. Finally, I'll describe an algorithm, a synthetic nearest neighbor, primarily for the causal model that I will introduce here. And again, sort of last few minutes, I'll spend some time discussing why I think matrix completion and some of the questions in causal inference have a nice intimate connections. So with that, let's get started. So here is one simple caricature example. So what I've done is that I've drawn a 5x5 matrix, so it's like 25 entries. And let's imagine that each entry underlying ground truth corresponds to a coin. So you have a coin, heads or tails. You got a bias. Entry ij, ideal entry ij is pij, the bias of the coin if you toss it. And what you're observing is just few coins tossed, some tail, some head, and some not tossed at all. And from this, I want you to go and fill up all the entries with the biases of the coin. Okay? So 25 biases you want to fill up from such sparse observations. Of course, if there's no structure, there's nothing you can do. So you hope and pray that there is some structure. One simple structure is, well, this is all the same coins, in which case you will just do the classical averaging. Matrix completion is a nice variation of this question, basically. And for this reason, it's been a great question that has driven lots of interesting work over past couple of decades. Just putting a little bit more formally, you got some ground truth matrix A, let's say M times N matrix. You have partial observations of it. That is, for some entries, you observe something, which is some noisy version of it. And again, I'm not specifying this yet. And for remaining, you don't observe anything. From this Y, you want to recover A hat so that A hat is close to A in some norm. Okay, and depending on norm, you might get different value out of this. Again, there's lots of details not yet specified, and I'll specify them in the model because there are lots of options. But that is roughly at the highest level what's happening. Okay. Again, please feel free to stop me any point of time. Now, again, so I'll just go very quickly. So traditionally, now maybe at least one of the earliest matrix completion question was in the paper by Goldberg et al., where they proposed this simple empirical algorithm collaborative filtering in early 90s. Then, for example, Nati Srebro and Yakola had a very nice paper earlier in the beginning of the century. There's a whole list where a typical example is what I would call a Netflix challenge setting, where you have a matrix. Think of these as rating matrix users and movies, and you're trying to sort of estimate the underlying matrix with respect to minimizing, let's say, normalized Frobenius norm. Here are just a few examples of non-typical examples. And again, my hope is that with this, you would find matrix completion more than just a Netflix challenge. So for example, if you take the classical multinomial logit model, which is a distribution over permutations, and you want to estimate the underlying parameters from pairwise comparison, hidden underneath work, which is with Sevung when he was at MIT, and Sahan, at its core, it's like you want a good handle of the spectral norm error, and that would sort of help you sort of recover the parameters of the model really well. There's lots of nice work subsequently done, some in the audience here itself, where folks are trying to get better approximation here, which leads to better approximation of the parameters. One of the things that we tried to do at MIT with a bunch of students, Anish Agrawal, Denish Shen, and Abdullah Alamar, where we tried to use some of these matrix estimation-based method as a way to impute and forecast time series, single and multiple time series data. And actually, Abdullah, for example, has gone ahead and built a nice database with prediction property or prediction capabilities within it. So if you like to play with actual software, is open source available at tspdb.mit.edu. Please feel free to play with it, give us feedback, that'll be great. Another way to look at matrix estimation is an efficient sampling. So again, you have lots of observations that you want to know, but if there's a structure, maybe only part of that you want to extract and others you don't want to, and then fill them up. And that's how we've used it in for reinforcement learning setting, where you want to learn a Q function. So Q function is state and actions. And it's if you view that as a matrix or bivariate function, then to approximate that, again, you can use this as a subroutine. And finally, close to this talk, there's a very nice literature in econometrics primarily on panel data setting. And panel data is primarily, or longitudinal data, is primarily the question there is of some form of matrix estimation. And depending on what norm you approximate, you will get different causal estimates. Okay. And I'll sort of indulge into this a little bit more as talk progresses. Okay, so hopefully I'll at least try to argue that this is an interesting class of questions beyond just a challenge. So let's sort of discuss the model. Typically, there's a generic latent factor model, which would say that the entry of the matrix that you care about is some latent function of latent factors associated with row and columns. And these factors are lower dimensional. While function is not something that you don't know, but hopefully it is well structured. For example, it's something like this, which will mean that matrix is low rank. Okay. But more generally, a function could be a nice C infinity function or a Lipschitz function. And all of those would give rise to a different model complexity. For example, Jemming has a really nice work trying to look at such a setup for the symmetric or graphon setting. Now, this is the ground truth. Question is, as far as the factors are concerned, or there is the U's and V's are concerned associated with rows and columns, one model is where you assume that these are sampled from some underlying distribution. Okay, and it's a nice distribution, as in, for example, in the context of graphon or stochastic block model. And that leads to very nice structure. It imposes nice structure on the factors collectively. Or if you believe in the adversarial setting or a given instance setting, then one would assume a condition such as incoherence condition, where effectively these are well-structured factors, so that if you observe any of the entries that give you enough information about the underlying factors. And of course, there's a question of that these two independent independent models, do they have any relationship with each other or not? And there is some really interesting connections that at least folks have found, but there is a lot to be discovered. For example, there's the notion of pervasiveness has something to do with this notion of incoherence, and pervasiveness is very stochastic property versus incoherence is very deterministic property. And there's a nice work in that paper. Okay, so for this talk, I'll assume that it's low rank, and I will assume, let's say, a deterministic property like this. Okay, you could sort of flip many of those things, and arguments would remain the same. So that's a ground truth signal that you want to recover. What about observation? So if you observe an entry, it's a ground truth plus some noise. I will call it idiosyncratic noise as independent, zero mean, but distribution may vary. Okay. For simplicity, let's assume a sub-Gaussian distribution or bounded distribution for the purpose of the talk. That's if you observe. The question is that how do you observe? How is the missingness determined? So in the original model, one would assume that all entries are missing at random, or MCAR, MCAR. Okay. What that means is that each entry ij is observed with some probability p. Okay. So for every ij, you flip a coin. If it comes up head with a bias p, you observe, otherwise you don't. And when you observe, it'll be like that. Okay. And then if it's not missing at random, so it's not MCAR, then it's MNAR. Okay, so this is a large model. Okay, as in, so we need some model within this to make sense. Otherwise, it's kind of terrible. So I'll open the brackets here, just to sort of point out a few nice references that introduce this or discuss this in detail are by Shebel et al. And then more recently by Little and Rubin. Okay, now in the MNAR world, so there's an MCAR where entries are observed uniformly at random. If not, in that massive space, there's one thing which I would call limited MNAR, okay, which has been now at least lately studied well. Here, what one would assume is that each entry is observed. So for each entry, you have a biased coin, but the bias of the coin for each entry is different. In particular, let's say Pij is the probability with which entry ij is observed, and you would require some kind of a minimum positivity condition. That is, minimum over ij is greater than or equal to some p star. Okay, and then there is a structure in this. So given this kind of a limited model, where again, entries are observed independently, but the intensity with which they're observed is different for every ij. And then sort of the intensity with which they're observed has some structure. And there's a minimal or positivity condition. So there's a bunch of nice works recently. For example, this just came out like a month ago by Bhattacharya and Chatterjee. The question is, what can one do this? Now, this is called limited MNAR because effectively there is a simple reduction one could think of, at least in principle, to the MCAR setting. So let's consider two MCAR problems, okay? So again, MCAR is just missing completely at random. Problem one, consider a matrix where whatever was observed, whatever was not observed, replaced by zero. Okay. And on that matrix, effectively now you got everything observed, nothing is missing. You run your algorithm, your favorite MCAR algorithm, and obtain X hat. Okay, now let's take another MCAR problem. Take the same data, But wherever you observe Yij, you replace by 1. That's your effectively, and wherever you don't observe, you replace by 0. So it's your mask. Okay. Again, everything is observed, like in stochastic block model. Okay. And then again, you run your favorite MCAR algorithm on this, you obtain M hat, and then just do this, these reweighting, and this is your estimate. And hopefully, if your MCAR algorithms were good, and because you have this nice positivity condition, hope is that this might work out. And this collection of work, now, of course, is a lot more detailed than just what I said. And that needs to be worked out. And lots of those nice things are worked out in this works. Okay.
So in particular, problem 2 is with Bernoulli's.
And again, sort of you want some kind of a nice estimation error because you're dividing entry-wise how that goes. So some care. For example, this one talks about 2 methods and establishes their consistency. Okay, so MCAR, limited MNAR. Now what I'll call is a causal model, and I'll argue that why this is an interesting model. So I'll spend some time just describing what this is. Again, as before, Aij is a low rank. Okay, if I observe entry, it's Aij plus some epsilon ij. Okay. Question is that when do I observe it? Let's call that matrix D. Dij is 1 if I observe it, 0 otherwise. This is a random variable. The entries may be dependent. Okay. And let's look at this, effectively this DAG. So entries of D may depend arbitrarily on the latent factors of all rows and columns. Of course, if I observe an entry, it's a function of this plus a noise. Now, there could be an additional edge here where entries that are observed actually are based on the noise itself. For example, let's suppose that here's what I'll do. As an oracle, in that original, say, 25 coin example I gave you, what I'll do is I'll flip all coins first. Okay, some of them are zeros and some of them are ones. Then I will go and reveal only those coins which are zeros. So from your observation perspective, you'll see everything 0, right? Now, that means that in that case, I am revealing entries after looking at the epsilon, that is the random outcome, and that's not allowed because that's terrible. I mean, then nobody can help you. So I will just simply prevent that part, but I will allow you to have dependence arbitrarily on this. Your probability of observing any ij could be 0 for that matter. And this DAG would imply that conditionally, what entries I have observed and the observed random variable are independent given the UVs, but otherwise they are dependent if I don't condition them. Now, why is this a reasonable model? So let's take sort of just one example like this. Think of, again, setting of Yelp, where you go to restaurants which you are likely to like, or which you're, hopefully you don't go to a restaurant which you're not likely to like. But then sort of you go there, and then you try it, and then maybe you reveal something or not, right? Similar in the context of policy evaluation, things like, let's say, what policy went into effect in United States for COVID versus what mask policies going in effect in United States in different regions for COVID. All of that depends on the characteristics of the region. Of course, there is a noise that is not determining whether what policy decisions are happening.
So this includes the case where the Yelp user reveals a review of a restaurant if it's the kind of restaurant they normally like, but not the case where they reveal it or not, depending partly on whether they did actually like it.
Yeah, so I think sort of exactly. So the question is sort of where in the model the epsilon is absolutely. Any questions about the model? So the only difference is how I'm revealing the entries. And again, this is confounding, as I mentioned, and of course, in this case, would allow you to have a lack of positivity. That is, some entries would never be observed, for that matter. So I'm going to skip this example because we know what confounding is, and I've given you a simple example. All right, so let's sort of look at what's known in the literature. And again, there are a few parts here. One is different types of algorithms, and then what sorts of results we know for different types of models. So there are a few algorithms. One, I would call it a spectral algorithm, optimization-based algorithm, or this non-parametric or nearest neighbor or collaborative filtering style algorithms. And I would say that sort of sum of square based method would hopefully fit into one of these two categories. One simplest spectral algorithm is singular value thresholding. There's you take the matrix, replace missing values by 0, or values like row averages or column averages or something more cleverer like that, and then do singular value decomposition and threshold it or truncate it. Optimization-based method would try to avoid looking at the missing values and simply try to fit factors based on observed entries. And then nearest neighbors are simply trying to use the observed entries for rows or columns and somehow compute the features from there and the nearest neighbor out of that. Now, there is a panel data method that's called synthetic control, and I'll briefly describe what that is. That evolved independently from many of this literature, as you can see from the date, and it has very similar flavor to nearest neighbors, but it's a nearest neighbors with kind of ordinary least squares involved. And I'll describe what that is, but for a very specific observation pattern. This is kind of a scorecard, if you like those things, for MCAR setting, where all of these are efficient algorithms, that is polynomial time algorithms and statistical guarantees. Now, it is possible that I might have missed some of the exponents or logs incorrectly in some of the places, because this was, I had surveyed it 2 years ago. So it's possible that something is wrong. But bottom line is that if you have missing at random, if you rank R matrix, then n times R times some logs is what you want as a number of observations to get consistent estimation. Many of those works are primarily for Frobenius norms, but there is a lot more progress now towards different norms. And again, I'm missing lots of entries. For example, one nice recent paper by Chen et al. Tries to obtain entry-wise Gaussian approximation. And then that enables entry-wise sort of confidence interval construction. In the context of MNAR setting, if you look at a panel data setting, and I'll describe what that is. It's effectively, if you look at the matrix, there's some number of columns are fully observed, and then some number of rows are fully observed. It's kind of a half T observation pattern. For that, there are synthetic control-like methods do work well. You can think of them as some form of limited MNAR setting. For the model that I describe of limited MNAR, is a few of the nice recent works there that try to establish consistency. And that's basically what we know for that setup. Now, what I'll do is just to, sometimes pictures are a lot more effective than all the theorem statements. So here is a simple experiment that I'm going to show you. Okay, so what this is a simple low rank matrix. For that low rank matrix, no noise, okay? What I'm going to do is, okay, so the factors are generated by sampling Gaussian entries for the vectors and then normalizing them. And then so now I generated matrix, look at all entries of the matrix, plot the histogram of it, and that's how it looks like. Okay, it's a shaded light blue. Then draw entries uniformly at random from it, for example, like that. So dots corresponds to observed entries, white correspond to not observed entries, and then plot their histogram. Now, of course, the number, absolute number would be smaller because I'm subsampling, but as you can see, the shape is similar. Just if I normalize and pull this up, they will sort of overlap on each other. So that's just entries of entire matrix and how that histogram looks like. Now, using these blue entries, let's apply the universal singular value thresholding algorithm and see the histogram of the filled matrix. And the histogram of filled matrix is quite skewed. And if you see, the frequency is much higher than what you would have hoped in the original matrix. Okay, so it's sort of actually, it is introducing quite a bit of bias even in the missing at random setting. And again, this is really nice setup because my factors are really nice, no noise. Okay. Instead, we applied there's a nice implementation of soft compute. There's a optimization-based algorithm. And as you can see, it hides the true histogram behind it. This really works really well. And the algorithm that I'll show you, which is primarily for causal model, but of course, if it's not causal, it's still part of causal. It also sort of works well and hides well. So this is missing at random. Now I'll keep the matrix same, but change the observation pattern. So in particular, this is limited MNAR setting. So remember, each entry is still observed or not observed independently, but with likelihoods are different. And there's a positivity constraint, in which case it looks something like this. And as you can see, there is a sort of pattern is skewed by design. And it's a low rank pattern matrix in mean. Okay, and so again, not normalized, but sort of it has these two bumps now. So clearly, sort of it is not MCAR. Now we apply USVT. At least visually, it looks better than before. But sort of look at the sort of the magnitude here. It's much bigger than before. So actually, it's a lot more skewed. Okay, so it's not improvement; it's gotten worse. There is a version of algorithm that I briefly described as a few slides ago, which is applying, let's say, USVT style algorithm twice. That would do terribly. It would sort of effectively be out of the chart, so I'm not showing that. Okay. We applied the optimization-based method, and again, nice thing about optimization-based method is it doesn't take into account what's not observed. It only looks at things that are observed, and again, there's a bias there. And this algorithm continues to work. But again, bias is small here. And then the last one, which is really this causal setting where some of the entries will have will not be observed and some of the entries will be observed. And the decision is made based on looking at the latent factors of users and, or let's say rows and columns. Okay, it is quite biased. The same trend continues for USVT. Now, the optimization based or soft compute does very poorly. And here I'm just truncating it because I know a priori what's the range in which it is. But this algorithm continues working. So there is something about how we observe and how we sort of incorporate observations, which will lead to sort of different types of outcomes. So now in the maybe remaining 10 minutes or so, I'll just describe what the algorithm is, what are the what guarantees we can provide, and maybe some discussion. Any questions?
So intuitively, you can do better in the causal case because you can learn something from an unobserved entry about its latent variables, whereas if the other algorithms treat it as giving you no information.
What I will the algorithm that I'm plotting there, which I have not described yet, it would not try to learn anything actually about unobserved things. It's only trying to sort of focus on the observed things only. And basic point is that if you just focus on observed things in a way that sort of you can convince yourself under this kind of model that the observations that you're looking at are not biased, then you can actually recover the signal. So in a sense, sort of look at less than more, a fewer of the observations in a nice structured manner, and they'll sort of take care of it. And again, sort of the idea is very simple. So it's nothing complicated. I do believe though there are better algorithms for this model than sort of what I would put out there. And again, sort of hopefully that will sort of lead to better sample complexity. Any other question? Okay, so now the algorithm. Okay, so first let's just quickly remind ourselves what is the nearest neighbor. Then I'll remind you what is the synthetic control. And then when you put those two things together, we'll get synthetic nearest neighbor. Okay, so I'll use picture just to describe, but again, sort of details of the algorithms will be skipped for obvious reasons. So think of, again, rows and columns. And let's say you want to figure out what this entry is. The typical nearest neighbor style algorithm would say that here is row I. Let me find another row that looks like this. One way to find that is look at all the columns in which they share entries. For example, these ones. And if they look close enough, which is my nearest neighbor on the observed entries, then I will look at the entry that that row has for this column, and maybe I'll just use that sort of and extrapolate it. And of course, in reality, you would try to compute multiple nearest neighbors, take the average, maybe use some form of weighting, do variation of it through kernel and whatnot. So that's a nearest neighbor-like algorithm. A synthetic control algorithm, again, originally proposed by Abadi et al. It's a nice survey he has recently, which tries to estimate counterfactual in the absence of intervention, and it's a very interesting panel data setting. So think of the following situation. Let's say one scenario in which here is the time when you implement a policy in a region. For example, let's suppose that we decided to try out what happens to Massachusetts crime rate if we imposed some form of gun control. Well, let's say before that, all the states had no such law. And this was the measurement of some kind of a crime rate measured weekly or measured monthly or whatever. Now, on this day, Massachusetts implements the policy. So whatever observation you're going to get on Massachusetts are going to be under a different policy than what we would like to know. And what we would really like to know is what would have happened to Massachusetts if it had not implemented the crime rate, sorry, the gun control. If it had not implemented the gun control, and if we would see what the outcomes would be, then we can compare them with the observed outcomes, where observed outcomes are under intervention. And now we have effectively this comparison setting, and now we can decide whether gun control really helped Massachusetts or not. So with that setting, effectively what one is trying to do is, for a given row, I want to observe outcomes in some number of columns, okay, which are completely missed. But assume that all the other states before and after continue to remain in the same situation. There is no policy implemented. So I'm going to observe all of the entries here, all of the entries here and here, and then I want to fill this up. Okay. So that's the typical synthetic control panel data, differences in difference before that, and other style of methods setting. And the algorithm there roughly goes like this, that you would think of these as your training examples. So these are my features, and this is my label. And then from there, I'm going to do effectively ordinary least squares, but with some structure on it, some regularization. And then once I learn this model, again, I know all of these things well because I just observed them. And now I will sort of utilize the model that I learned between this row and other rows and extrapolate it. Okay, it's very simple. And this is called synthetic control. And at least in the original work, this was required to be non-negative weights, because the idea was that Massachusetts is 80% like California and maybe 20% like Texas. And so sort of you want to sort of keep the non-negative weights that add up to 1. One of the things that sort of early on that sort of with Dennis and Jahangir, we found that instead of doing that, if we simply utilized matrix estimation-based denoising, actually it worked much better in many of the empirical settings. And you could sort of say something more formally about that. And it's sort of primarily it becomes PCR. So now I'm going to sort of put those two algorithms together for the problem that we were discussing. Okay, so just nearest neighbor with the synthetic control. Again, I'm going to show you with the pictures, and I'm going to skip lots of details. Imagine that this is the entry I want to fill, and this is the type of observations you have. So there's a row I, column J, that's what is missing. There's some entries you observed in row I, some entries you observed in column J. Now I've sorted it so that it looks nice and clean. Okay. And now let me call the entries in which row I have observed something. Let's call these columns NC of I. For column J, the entries that I have observed corresponding to those rows, let's call this NR. Okay. That forms this square for me. Okay. Now, inside that, let me identify A square S, where I've observed everything. And this is what I was saying, that I'm going to now ignore everything else, but just use this square. And now I'm going to sort of treat this as effectively a synthetic control-like problem with variation on that with nearest neighbors. In particular, what I will do is that let me think of these entries as my labels. These are my features. I'm going to learn a linear model between them. Just as before, that is, this entire matrix I will denoise using singular value thresholding, just this part. And then I will try to learn linear model. That's effectively I'm applying principal component regression. Use that with these as my, let's say, the test features now, and then sort of estimate. Yeah.
S fully observed or not here?
S is fully observed.
Okay, so where do you use singular value thresholding? What do you still?
Only on this one.
Oh, but it's not fully observed. Here.
So there will be noise here, right? So while this is a matrix, which is fully observed, but it's a noisy entries, a noisy observation there. I've got lots of epsilon. So remove the noise.
Oh, so okay, so it's just PCA.
Yeah, PCA. Now, of course, this is only one entry I've got. In typically nearest neighbor, you want many things. So what do? Effectively bootstrap-like things on top of this. So you will sort of have multiple squares out of these, and then sort of create multiple estimators and then average. And once you'll do that, then sort of you will get nice confidence intervals for each entry. So in yes,
Finding it as a likely problem.
exactly right.
Okay, so it's hard, right?
Okay, good. So it is hard, and all the empirical results I showed you, we simply sort of ran a simple greedy algorithm to do that. But it's a good point, and that's why sort of results that I'm proving here really are assuming some kind of witness is existing, and so they're not sort of the strongest form because you're not sort of fully utilizing all the information you can. Excellent.
But the chances are better of this kind of rectangle existing in the causal model than in MCAR, right? I mean,
so
correlations between
that at least intuitively definitely makes sense. So here what I'm going to do is I'm going to sort of state a theorem with certain sort of assumptions. So this is just a usual. The key thing is this observation pattern. And in particular, I'm saying that let's say that there exists an S, which is say k by k raised to 3 by 2. Okay, or other way around. I mean, because the dimensions don't matter. If you have that for a given entry ij, because for every entry ij, this is different. For a given entry ij, if you have this, then with high probability, you would be able to get a bound like this. And again, so the high probabilities with respect to k, not with the latent dimension. Now, one might ask the question that, does this kind of a square have a chance to exist, right? So we say, okay, I don't know sort of generic MNAR model, but instead what I'll do at least go back and see what happens in MCAR setting. So for example, if you have density like this, n by n matrix, a density like this, then it would effectively result into an error bound like this for every entry. Again, I don't think this is just a very simple calculation. So definitely this can be tightened. Because you can sort of do a multiple estimation out of it and then sort of get averaging. This averaged estimation will satisfy nice nice central limit theorem also as k increases. And this sigma twiddle k, I'm not writing down the formula, but effectively it's coming in because different entries might have different variance, and then they are combined with the model that you're learning. So it'll be that standard deviation. Okay. All right, and I've got 1 more minute left, right? Okay, I'll skip all of these things. Dennis took on to himself and said, you know what, I'm going to go through the whole zoo of matrix estimation algorithms that are out there. So he actually looked at every code that he could find online, and then sort of these details are in the paper. I'll leave you with that. I'll just sort of do one sort of quick discussion in our land. So there are many ways to think of causal inference. One simplest way to think of causal inference is, at least the challenge of it, is that you got some outcome that you're interested in. You got some intervention that you care about, and you got some confounders, sometimes latent, sometimes observed. Okay, and ignoring the noise, effectively the outcome is some function of intervention and the confounder or latent factor, latent confounders. And when it's observed setting, the interventions are also dependent on your confounders. If it's experimental, then there is no such dependence, and that's why I'm putting dash dash line. So, for example, if I want to find out what would be the effect of an intervention A over entire population, I say, well, let's sample individuals from entire population, which is effectively sampling you. Okay, and all of them get A, and I observed this, and this will help me understand the population level potential outcome. But what if I say that in this particular, there's a person, it's a person guy, I don't know corresponding the latent confounders associated with him or characteristics associated with him. And for him itself, I want to know what happens to him under A, what happens to him under B, what happens to him under C. That would require me to know this function F and U associated with him, right? Those are the two things. If I know F and if I know U, I'm done. Now, of course, you don't observe all the entries, so you have to somehow extrapolate it. This matrix completion-like setting says that this function that you have effectively factorizes nicely, which means that even if you observe at few places, you can extrapolate it to the all possible rows and columns or all possible interventions and the individuals. And you don't need to know the latent confounder associated with individual because you are somehow learning relationship between them through other rows that matter for the purpose of your predictions. So in a sense, at least when you have lots of observations available for each individual, or high dimensional observations available for individuals, then maybe this might be a way to at least solve some of the causal problems. And definitely, as you see this already sort of seems like solving high dimensional mixture problems for that matter. And so anyways, I'll leave you with this last remark and questions.
So one or two quick questions before our break. I mean, we have a 3-hour break starting now.
Thanks. So I thought it was interesting the way you diagnose the performance of different methods by looking at the histograms of the recovered values.
Yes.
And when I see this, the first thing I'm tempted to do is to just use it and, just to be sure at least that I'm doing good on this thing that you're actually measuring. But are there any methods that actually try to calibrate matrix recovery? Because you could estimate the distributions of your censoring, and you could estimate the distributions that you could deconvolve the distribution of the observations, and then just uses like some penalty that just forces your method to actually stick to that. And so I'm guessing you're not using this at all,
no.
But do you know if there's any methods that try to actually stick to that?
It's a great question. I don't know.
Okay, thanks.
More questions?
Yeah, actually related to the previous questions about this histogram, is that because your method works better in terms of infinity norm? So you have an entry-wise control, so it's kind of looks much better than, say, for example, universal single variance thresholding, where there is more on the Fabry norm.
I think there's more than that. So for example, this soft impute style method, I think it's because of observational pattern. So soft impute like method that we had used it to learn the Q function, where in that setup, the way sort of observations were obtained were designed because we were interested in sort of efficient sampling. And while there's no theorem for that setting, to the best of my understanding, it provided really good entry-wise guarantee. So I would believe that, I don't know if anybody has done empirical analysis, but soft impute like method in the MCAR setting would provide really good entry-wise or L-infinity norm guarantee. But I think in this case, it sort of ends up doing poorly.
Actually, I have another question. It's okay. So about the theorem that you're showing, so about this click,
Yeah.
you're finding this by click. Yeah, maybe I missed that. So I thought that in this, if you do not observe a lot of entries, then the size of the largest by click you can
Will be
find is
small.
probably very small, like even constant log n or 2.
That's correct. So that's why sort
Right.
of I wanted to sort of at least show that simple calculation. That is, at least there is some regime where the fraction of observed entries are is going to 0. Still, the sort of the number of biclicks that you would observe with each of the size would be sort of large enough. So that was that sort of thing. There's a the observed each entry is observed with a n to power minus delta, and then you would be able to, with whatever sort of biclick size you observed, apply the method applied, it will give you entry-wise error to be delta to power 1/12. But again, I think it's I don't think it's a fully tight analysis. Maybe 1/12 could be improved to 1/3. But I don't know if you can do better than that.
So one more question.
Okay. In the end, does it give you a lowering matrix as an estimate, or is it like a nuclear norm minimizer setting? where the-
Good. So we did
it's
not impose the low rank constraint on it
It's more flexible
because
right?
it's sort of per entry estimation.
Right. It seems like that might be why one of the reasons why you're gaining is you are allowing it to be more flexible like that, as opposed to other methods are restricted to be low rank in this comparison, right? They're exactly low rank.
That's an interesting point. I don't want to immediately agree to that for the simple reason that underlying true matrix itself is also low rank that you're trying to approximate.
Right, right.
So,
That's
but
also
maybe
true.
sort of your point is sort of because algorithm has flexibility, somehow that flexibility allows it to discover the right thing rather than.
Maybe, yeah.
It's a great point. Yeah.
All right, let's thank you again.